Right, so two loop integrals for the production of two heavy bosons and a jet at the LHC. And so what's the goal? So the idea is that we want to compute, as we heard in the previous talk, we want to compute Feynman integrals in a way that make their analytic structure transparent. And but also, if we want to do phenomenology with them, we need to be able to evaluate them in a stable and efficient way. And so we have to keep these two goals in mind. I will focus here on this set of integrals that we need for, so there are 5 external particles, 2 of them are massive and all the propagators are masses, but a lot of what I'll say here holds more generally for these type of integrals with a lot of scales. And a point that I'd like to make is that this should be easy and boring because we're not asking for a lot. We're describing processes with 3 particles in the final state, which is not a lot, and at the second order in perturbation theory. So I find it a bit surprising that we cannot do this easily yet. Not only that, the functions that appear are really the ones that we've been saying for a long time that we understand very well, so we should be able to compute this easily. Now, in reality, I worked for quite some time on the equivalent process, but with only one massive external leg, and this took us several years to complete. So it's not true that it was very easy and boring. Although I have to say that for these ones that I'll talk about today, we have much better tools, and it actually was very simple to do this calculation. And I will also like to highlight, and I'll do it again during this talk, there was first explorations on this type of integrals done in this paper. I think Shafeng is here, and we'll give a talk about this later in the week. And as a bonus, also because I know this audience likes a lot n equals 4 super Young Mills, I will also present some application of these integrals to compute double Lagrangian insertions in Wilson loops. So the motivation for this talk was already given by Lorenzo, so I'll go over it very, very fast. If we want to compute percent level prediction to cross-section or observables, we need to go to at least the second order in perturbation theory. On the amplitude side, that means that you need to compute two-loop diagrams. Again, these parts, the tree-level amplitudes are under much better control. We can do them systematically for a lot of processes. It's not that it's easy to do, but it's at least, it's essentially a solved problem. As Lorenzo already pointed out already, we don't need only the amplitudes. We need to then integrate these amplitudes over phase space. And when we do this integral, I mean, this artificial splitting of the integration over phase space and the amplitudes introduces some singularities. And so you need to handle these singularities somehow. And for the purpose of this talk, this means that we will have to compute these integrals in dimensional regularization. It's not sufficient to know them for d equals to 4. We actually need to compute them in 4 minus 2 epsilon dimensions, and then we expand it around epsilon equal to 0. And I point you to Chiara's talk for more details about this procedure, which is very complicated, but I will not talk about. There's another, so we want to compute amplitudes, and there's another natural factorization in amplitudes, which is you can decompose them into master coefficients and master integrals, and master integrals will be the focus of this talk. The master coefficients are process or theory specific, and they typically are rational functions, or they have some square roots, but they're typically rational functions. The master integrals, they only depend on the kinematics of the process, and they involve more complicated functions like logarithms, dilogarithms, or elliptic integrals, as we already heard in Lorenzo's talk. So what I'll try to explain in this talk is that it's very useful to consider Feynman integrals as vector spaces, and the key word here is integration by parts relations and master integrals. I'll explain how we compute these multi-scale Feynman integrals. Again, what I'll say applies to multi-scale integrals. If you want to compute integrals with fewer scales, there's other techniques that are perhaps better than what I'll talk about, because the challenges are different. So I'll describe how to compute multi-scale Feynman integrals, and what I mean by compute is really to get access to this analytic information about the integrals. And this is where you would stop if you want to do some formal study like n equals in n equals 4 super Young Mills. Now, if you want to do phenomenology, you also need to efficiently evaluate these Feynman integrals. So I'll also say some things about this. Okay, so let's start about how we compute the Feynman integrals. Sorry for the heavy slides, but what I want to do here is essentially summarize what Lorenzo already presented in his talk, is this idea that Feynman integrals should be viewed as a vector space, and the given, you should really think about these as families of Feynman integrals. And the integrals in a given family are related by IBP relations. The IBP relations are very simple. They're just the fact that in dimensional regularization, the integral of this derivative is 0, so there's no boundary contributions. And so this very simply leads to linear relations between integrals with the different powers of the propagators. I'll consider here the propagators as having integer powers. There's also applications for cases where the propagators are not, the powers of the propagators are not integer, but that's not relevant for what I'll talk about here, but people also study that. Importantly, the number of master integrals is always finite, and that means that if you want to solve a family, you only need to compute a finite number of integrals. Each family so defines a finite dimensional vector space, and we didn't coordinate on the wording, but we came out with exactly the same sentence that some bases are actually better than others, and we will use this in this talk. I should say that so the setup of integration by parts relations is a bit strange because it's very easy to write down the IBP relations. Solving them is very complicated in general. And but there's a lot of public codes that do this for us, and there's many of the market. Some are better at some cases. For some cases, others are better for other cases. But there's a lot of choice on the market. However, despite this, they're really a bottleneck in many applications because as Lorenzo also pointed out, the size of these relations can become very, very large, and so handling these expressions is complicated. To the point that we try to use only partial analytics when it cannot be avoided. Otherwise, we bypass these large analytic expressions with numerical evaluations. And if you want to simplify your life, you can use these numerical evaluations with finite fields where numerical calculations are exact. And so you get exact results out of your evaluations. So let me give you a flavor for how complicated these things are. So here is a first example. So this is the integrals that you need to compute if you want to do 5.1 mass scattering at 2 loops. And what I would like to highlight here is the difference between planar sectors and non-planar sectors. So these are, each picture here does not represent a single integral. Each picture here represents one of those families. So any integral inside that lives in this family is related by IBP relations. And the numbers in red here represent the dimension of this vector space. So you see that in the planar sector, what we call pentaboxes, doesn't matter why, you get up to 86 master integrals per family. Now, when you go non-planar, this number tends to become much larger. I don't know why it's like that, but it explains why, if you look at the timeline of the papers, it takes much longer to get to this to compute the non-planar sectors than the planar ones. As a second example, which is the subject of this talk, these are the integrals that you need to consider for 5.2 mass scattering, and I'll focus on the planar limit, and I'll compare 1 loop versus 2 loops. So these numbers here are really typical of 1 loop integrals, where you have order 10 master integrals, 20 master integrals per family. Once you go to the 2 loop case, you get order 100. And you see that this really fits very nicely between the planar 5.1 mass case and the non-planar 5.1 mass case. So this is really at the intermediate level of complexity between the planar and the non-planar sectors of 5.1 mass. Again, here I can be a bit more precise. This family had already been studied in this paper that I'll also mention later in the talk. And this is the set of integrals that we've computed and that will appear soon together with Dima, Vasily, and Simone. Okay, so our goal is to evaluate the integrals around d equals 4 dimensions. And what we want is not, again, an expression for them for general d. We really want an expansion in epsilon. There's many ways to compute Feynman integrals. You can do some analytic numerical integration of parametric representations, but transforming it into a differential problem really uses the fact that these things are defined vector spaces. As we saw already in previous talk, if you have a set of master integrals, it's close on the differentiation. If I compute the derivative, all I'll do is I'll change the powers of the propagators. And so then I can use my IBP relations to reduce it back to a set of, to write it back into my set of master integrals. And so the IBP relations are rational in the kinematic variables and in the dimensional regulator. And so this matrix is actually not that complicated. It's just a matrix with rational entries. Despite that, for a generic basis, it's not clear you've gained a lot by doing this because you've just transformed an integration problem into solving a differential equation. And if you don't know how to solve this differential equation, they can be very complicated. I mean, these things, again, have 100 entries. So this is a 100 by 100 matrix. It can be very complicated to solve, right? And this is where you can use the fact that some bases are better. And as Johannes taught us some years ago, if you find a pure basis where the differential equation is in canonical form, then you have a differential equation that looks much nicer. So in particular, epsilon comes out of that matrix. So that means that solving this differential equation order by order in epsilon becomes very simple. And also the kinematic dependence on this matrix is only through these D-log forms. The AIs here are just matrices of rational numbers. So these WI contain all the logarithmic singularities, all the branch cut information about your functions, and this is what's called the symbol alphabet. And if you find such a form, this is what I mean by exposing in a useful way the analytic information that lives inside these Feynman integrals. Unfortunately, we have no general algorithm to find the pure basis. There's some automated codes, but they have a lot of limitations. And but one tool that we have to do this is to study their leading singularities. And this is also how you can see how square roots enter the game. So if you look at the very well-known case of the three-mass triangle, this is how it looks like. It has a 1 over a square root, and then it has this function here, t. This function satisfies a differential equation in this form, so I would need to know how to normalize my integral before I can write a differential equation in this form. So the idea is, can I determine delta 3 without computing the integral? Because I don't want to have to compute the integral. I mean, the goal is to compute the integral. So I would like to determine this before I actually write my differential equation. And indeed, by studying these leading singularities, you can compute this thing as some residue of the integrand. And by studying other properties of leading singularities, you can actually build integrals that have this form. Essentially, they should have a unit leading singularity. As an example of how messy this can be, for this particular set of integrals, so the two-loop 5.2 mass integrals, you have to handle 44 different square roots. And as an example, this is a large number. If you only have one external mass, then we only have 10 square roots to deal with. And so these square roots, some of them have some nice physical meaning. So for instance, the 3-point Gram determinant is something that you would encounter just by studying the kinematics of three particles. You also have the 5-point Gram determinant. Again, this is something that you would expect, but then you have some more mysterious things that show up that you can compute as leading singularities of some integrals, but that have less of a nice physical interpretation. So there's some type of square root that shows up in 4.3 mass already. So this is associated with this diagram. And then you have new square roots associated with 5-point diagrams. So with this diagram and with that diagram that show up for the first time here. And all these things appear in several permutations, and that's how you get to 44 square roots, which is, again, something you have to deal with. How do you compute these leading singularities? So it's not always easy, and it's a bit of an art. So these are, I'm taking here as the example, these two 5-point, the diagrams that give these two new 5-point square roots that show up. So you can do this loop by loop. So you just, the idea again is that you put some propagators on shell and then you integrate over that. And then you have, so you can do this loop by loop. You start with one loop, you put all the propagators of that loop on shell, and then you go to the other loop and you do the same. And as long as the things you're integrating over look like Feynman propagators, then you're happy. But you see that that's not always the case. For instance, here, if I first integrate out the red here, so I have a box with 4 massive corners, and this thing, the leading singularity, is some square root of some Gram determinant, turns out to be very close to this one. Anyway, something that doesn't look like a propagator. So I would not know then very simply how to do the next integral over that to then go to put the other things on shell to be able to identify the leading singularities. If I do it the other way around, though, if I start with the triangle side, then this thing looks more like a propagator, and I can actually go all the way to the end. So this is the case for this diagram. For that diagram, there's no path that is simple to compute, and indeed we will see that this square root caused a bit of trouble in the construction in solving these integrals. So you can do it, but you need to work a bit harder to compute the root. Also, as a side comment, which is something that people, I don't know if you, I found it surprising because I had never seen it before. There's actually some diagrams that come up with 2 square roots in the normalization, and this is the first time I see this. Again, this is the diagram that Schaffing and collaborators had already looked at. Okay, so the goal is to get a differential equation in this form. This is very difficult to do analytically. However, you see that all the kinematic dependence sits there. So if the WIs are known, then I can determine these AIs just from numerical IBPs, because these AIs are just numbers. So then if I can evaluate the right-hand side of this equation numerically, it's easy to believe that just by some linear algebra, I can determine what these AIs are. And indeed, the WIs just give you the singularities of Feynman integrals. So they're not really they don't have just something to do with the differential equation. I can try to study them from a different perspective, which is from Landau conditions. And this allows me to factorize the work of determining the AIs without actually computing the differential equation. And this is a very active area of research in this community. There's many ways to approach these things, like coaction, again, solving the Landau conditions, principal A determinants, prime determinants. There's many people working on this. But I would like to highlight these two papers which made this very concrete and useful in practice, because everyone knew that we should solve the Landau conditions, but doing it in a way where we actually can do it for complicated enough cases and in a way where what you get out is useful in practice was not so available previously. So indeed, in our calculation we used this paper, and they have a very nice mathematical package called Bikov letter, which allows you to you give them a diagram and you ask for the letters and something comes out. And in fact, most of it comes out. We have to compute all these families, and for the ones in green, all of the alphabet comes out. For the ones in red, something was missing, and it's related to that square root that I had in my previous slide, so this square root here. But talking with Xiaofeng, I think this is not a limitation of their approach; it's just a limitation of the package that they made available. And it's precisely to do with the fact that to identify that leading singularity, you don't always have linear residues to take. So this is how so this is a slide that summarizes the information about the alphabet for these integrals. So this information you've already seen. This is just the number of master integrals for these different families. And this is the dimension of the alphabet for those families. So if you want, this is the dimension of these matrices here, AI, whereas this is the number of terms you have in this sum. So put together these things give you a feeling for the complexity of this problem. Overall, we have 570 independent letters. So this is where if you take the letters that show up in these integrals plus all the closing and the permutation of all the massless and massive letters. And you can classify the letters in terms of even letters. So these are letters that are polynomials or rational functions in the kinematic variables. Odd letters, so odd letters in one square root, which take this form. In this case, again, there's 44 different roots that can appear there. And then you have odd letters in two square roots, so that take this time. And again, this form. And again, this package was very, very helpful in making this calculation go much faster. Most of the letters were obtained from here, and we had to construct only mostly odd letters. There was one even letter that we had to fix ourselves, but this really makes things much easier, especially because odd letters are very easy to construct. Okay, so now let me say a few words about how we evaluate Feynman integrals. The first thing you need to do is to evaluate a boundary condition, to find a boundary condition. There's a very elegant way to do it, which is to realize that the information about the boundary condition is already in the differential equation. So a general solution to this differential equation will be singular when any of these guys vanish. But we know that Feynman integrals don't have all those singularities. So by imposing that, you can actually constrain your initial condition. And we've done it. I mean, this has been done by many people, but I want to highlight that it can be done also for these complicated multi-scale calculations. So we did it for the planar sectors for 5.1 mass integrals. Now, in 2022, there was this AM flow approach that was proposed. So the idea here is to take a Feynman integral, go to a very non-physical limit where all the integrals become tadpoles, and tadpoles are known to 5 loops. So then you can evaluate the integrals there, and then you evolve back to physical points. And by doing this, you can actually obtain high precision for pretty much any integral that you would like, say to order 100 digits at any point that you would like. And this is very useful because that's what you want as an initial condition. You want the evaluation of the integrals at one point. And if you want to do phenomenology, that's all you need. In our case, we could evaluate these things, all the integrals at these 2 points, so one in the Euclidean region, one in the physical region, and we got 80 digits out in around a week, and then this is sufficient for any phenomenological application. Okay, so how do you solve these things? So the idea is to start from, you can start from chain iterated integrals. You can have numerical solutions of the differential equations. Lorenzo also already mentioned these two things. You can write the solutions in terms of special functions like logarithms, polylogarithms. The issue here is that these roots make it very hard to do in practice. And also the expressions that you get out are not the most convenient because you have to introduce spurious singularities to write these in terms of polylogarithms. And then you get expressions that are only valid in a very small subset of in small regions because of this very complicated branch structure. So we don't take, so instead of that, what we do is we use this idea of pentagon functions. So the pentagon functions are essentially recycling the idea that you should work with the basis of functions, And whereas master integrals are linearly independent before expansion in epsilon, when you start expanding in epsilon, you get extra relations. And the idea of pentagon functions is to make these relations explicit order by order in epsilon. So this has been done already for some time for 5-point kinematics, and we propose an improved algorithm for the 5.1 mass case. And the idea is to solve the differential equation in terms of chain iterated integrals. The advantage here is that we know very well the algebra that these chain iterated integrals satisfy. We can choose the components of Feynman integrals to be basis functions. And then you use symbol technology to write everything in terms of these bases, and then you implement everything in a nice C++ code. So essentially, you have a C++ code that is tailored to solving this particular type of integrals. And then you can get very nice numerical evaluations. So you can get, for instance, this is for 5.1 mass. We're still working on the 5.2 mass cases, but you can evaluate all the integrals that you will need in all of the permutations in 3 seconds. You can even have, if you have places where you lose precision. So here, this plots the number of correct digits sampled over some 100,000 phase space points. So you want to have more points to the right where you have a lot of correct digits. And you see that there's some places here where we lose precision. If you have a good control of the analytic structure, it's very easy to catch these points and then have a curve that looks much nicer. You can build a very nice rescue system. Of course, you pay a bit more. It becomes a bit more expensive to evaluate, but you can choose whether you want something that's very fast and you lose some precision, or if you want something that is very precise, but slightly slower. In any case, you have something that is ready for phenomenology. All right, so let me have now the last 2 slides. I will talk about an application of these integrals to a calculation in n equals 4, which we're using as a check of the validity of the correctness of the integrals that we've computed. So Lagrange insertions in Wilson loops have been studied for a while, in particular because they're connected to integrands of MHV amplitudes. So the idea is to so you have a Wilson loop and you put some Lagrangian insertions on it, and then you compute this thing. Now, by themselves, they are divergent because you can have singularities at the cusp when you integrate over this. But so you can define this ratio, which is better behaved. And okay, so you can look at this object, and this object has been studied extensively. In particular, if you have a single Lagrangian insertion, both in the weak and strong coupling limit, and so you can expand this function in powers of the coupling. And it turns out that then the kinematics underlying this, the functions that appear in this expansion are just 4-point kinematics. This is because in principle you would have 5 variables, but then you can take 1 point to infinity, and then this reduces to 4-point kinematics. Again, this has been studied by a lot of people, and there is a conjecture about the positivity of these coefficients in the expansion, and this has been tested up to 3 loops for the single Lagrangian insertion. And you can show that this happens. So with the integrals that we have, we can now start looking at two Lagrangian insertions in the Wilson loop. Again, the kinematics are that you would start with 6 variables and you take 1 point to infinity, and now you have 5-point kinematics. These are not generic 5-point kinematics, so there you have 2 massive legs, but they're not generic 5.2 mass kinematics, because these two, so in our convention, this is P4 and P5. P4 squared is not 0, P5 squared is not 0, but P4 plus P5 squared is 0. And in that sense, it's a degenerate limit of the 5.2 mass kinematics. So we looked at these objects. You can expand it leading order, then you get just a rational function. Again, this is related to the integrand of MHV amplitudes. You can study it at weight 1, where you have 1-loop integrals, so things of this type, the pentagon and boxes to compute. And then you go up to weight 4, so 2 loops, and then you have this object to compute. And this is one of the families that we had computed as part of the complete set of 5.2 mass integrals. A test of our calculation is that this is finite and pure, that the result is finite and pure, because the way we do the calculation, so you have these IVPs, like Lorenzo told you, they mix UV poles, IR poles, and so on, and you put everything together, and the thing that comes out at the end, it should be free of any singularities, and it should be a weight 4 function, and this we could already verify for the 2-loop case using our integrals. Not only that, we can propose a new conjecture. This is valid in a region defined by the Amplitude, like the previous one was. And we conjecture that this holds, so that if you expand here for L equals to 2, so each term in this expansion for L equals to 2 will behave in this way. It's trivial to check that it's true for L equals to 0. for L equals to 1, it's not trivial to check. And in fact, it holds very non-trivially. And we're working on finishing the L equals to check. Okay, so as summary, I think we have very mature tools that allow us to push the state of the art in this calculation. We have thin already available for 5-point massless and 5.1 mass processes. And the progress in 2-loop 5.2 mass processes was much faster, I think, because of these tools that we now have. The new results that we obtained with Fino in mind are also lead to new formal studies, for instance, Lagrangian insertion in Wilson loops. And this is related to the discussion that for the future, I think this is related to the discussion that we were having before. Is our pentagon functions actually a good basis? We know that they're not at one loop. Indeed, we should include some rational functions to have them behave better in some kinematic limits. But this is precisely the discussion we were having before. Aside from that, there's other challenges ahead. What if the singularities are not all nice D-logs? Well, you have elliptic integrals and beyond, and there's a lot of developments in this direction, but we're still missing all the heavy machinery that we have to deal with the D-log cases. Thank you very much.
Thank you for a wonderful talk. We have time for 1 or 2 questions. Lorenzo.
Nice talk. Thank you, Samuel. I'm curious. So since you use like the same flow approach, so you have like a random point that you choose in the bulk somewhere, right? To get the boundary condition, I guess, from there, right? And then you evolve. So now if I want to use these results to see analytic simplifications of the amplitude, right? So in principle, I should carry information of the boundary on the boundary condition somewhere, right? So does this matter on whether you start, say, from a nice point where everything is pi squared and theta values, or you start from a random point in the way the amplitude looks like at the end?
So no, because this is all packaged in the this is all packaged inside of this is all packaged in the relations between the functions and the basis of pentagon functions. So the zeta 2s and so on still appear, but they appear not as the boundary condition, but they appear as the relation between the different pentagon functions. So you have some black boxes that are pentagon functions, and then these different pentagon functions are related by, so when you write all the integrals in terms of the pentagon functions, then things like pi squares and so on will appear. So these things still show up. Now, the point that we pick is not random. It's a point that should sit in a nice place in the bulk of the physical region, such that you can reach all other points in a fast enough. But it's not a point where things evaluate to zeta values or. Yeah.
Thank you. In the interest of setting a good example for the future session chairs, let's thank Samuel.